closing here. The rest of you, please, if you arrive late, register your attendance at Univirtual to be checked there. Okay, minimizing here, going to the book. We have to do at an hour class, well, 43 minutes now class. If you can help me, please, Mr. Our link student, who is our link student, Mr. Vega. What is the last page that we did?
Teacher, sorry. Garay Suarez.
Mr. Garay, etc. Just register your attendance on the yes, because it's 18 minutes after 10, so it's enough time. Now,
mi audio no funcionaba.
So you were send me a by chat. Type your name, but your last name first. So Garay, Suarez, Daniel, present, no? In order to revise it afterwards.
Sorry, teacher.
No, don't worry. If your message arrives before 10:20, so you have 1 minute only, I will accept it. Next, let me check the books and material. Yes, Mr. Vega.
Page 109.
Didn't we start with a new book with Oxford English for Electronics yet?
No, teacher.
Oh, okay. So we finish with the book of basic English for computing, because we cover finally even issues for computing. Okay. So now let's start with the new chapter that is from the new book, English for Electronics. It's on the campus now. You have a Univirtual webpage or a Moodle, sorry. Hope that you have the book, not to waste time trying to open or downloading it. Electronics, we are going to start with component values. That is page 21, unit 4 of that book. Going to share with you the page. And this is going to be really fast because we need to take advantage of the time every minute. Just in case, Mr. Acuña, your camera is off. So now getting on, share screen. Here we go, share sound just in case, and sharing. So this is our new book, the book that we are going to use. That is, it's already on Univirtual. This is Oxford English for Electronics. So now all the topics are not going to be now computers or data or information, but are going to be connected to electronics. Certain number of sessions, then we are going to move to electrical mechanics. Okay, so in this book of electronics, we're going to see also chapters that corresponds to that are connected to communications, to telecommunications. So page 21, component values. Component values is connected to the first devices that we study in electronics or in electrics. No? Those are, for example, resistors. And for resistor values, you know that the form of coding is connected to colors, right? Using color bands. Why? Because as the resistors are such small devices, it is not convenient to put letters or numbers in order to give the value of each device or component. In that way, they establish a rule or a code of colors, where 0 is black, and what else? Do you remember what color is represented by 1? Remember?
Gray.
No gray. Black is 0, and 2 is red. So something between red and black.
Brown, teacher.
Right, brown, sir. Very good. Brown. Yes. Oops. Sorry. Capital letter. I'm not angry. Huh? It is yes, brown. Yes. Then we have red, orange. What is number
Yellow.
4? Number
Yellow.
5. Very good, sir. Yes, yellow. So here we put yellow. Yes. Now green, blue, violet is number 7. Number 9 is white. So something between white and black, that would be number 8. What is it?
Gray.
Gray. I'm going to put in black, but it's gray. That could be written with E or could be written with A. So gray with E exists and gray with A exists too. And they both mean the same, the color. So we have black, brown, red, orange, yellow, green, blue, violet, gray, and white. Yes. And apart from that, we have the indicator itself. No? So as you remember, the first band indicates a digit, the second band indicates another digit, the third band indicates something else, and the fourth band indicates the tolerance. No? So the first digit indicates is a value. So we put here, this is a value. So a number. This second band is another value, value 2, for example, value 1, value 2. The third one is a multiplier. The multiplier means the number of zeros. And finally, here, not to put this slowly. Yeah. Oops. Oh, no. Really? I'm deleting everything. Okay, but I'm going to say that. The last one is the tolerance. Let's see if I put here tolerance. And the tolerance is marked by other group of colors. No? Red 2%, gold 5%, silver 10%, and no band. If you don't have any band, is 20% tolerance. The higher tolerance, the less price that you have to pay for this component because it's less accurate. Accurate means exact. So the smaller tolerance means that the resistor is more precise, more accurate. If you have greater tolerance, means that the resistor overlaps other values too. Now, reading the resistor code. Here we have the text where all of these theories explained. They're here. We have here the text where all of this is explained. For example, they say resistors are coded with color bands. Continue reading, please, Mr. Let's see, Mr. Rojas, Carlos Rojas. Carlos Rojas.
Yes, teacher.
Tell me, help us here, please. Can you read that part?
Yes, resistors are coded with colored bands and to ease the problems of making such small components.
Okay, thank you very much. Now, Mr. Miguel Vergara, can you help us reading the next paragraph, the numbers?
The numbers corresponding to the 10 colors used and the values per positions are shown above.
Above, yes. Now, let's see, Mr. Saavedra, thank you very much. For example?
For example, 180,000 ohms is coded but with the first digit brown, then gray, and finally yellow. The fourth band indicates the tolerance that the value has with respect to the stated value. For example, silver indicates 10% tolerance, meaning that the 180,000 ohms could vary between 100,000 plus
you
or
can
less.
Say more or less. You can say more or less.
Okay, more or less 18,000 IE.
This is this is, no? Or in other words.
Okay, I didn't know.
Yes.
162,000 to 198,000.
Okay, thank you very much. I'm going to take advantage of this or the opportunity to explain you this. In some reading, when you have, for example, e.g. comes from the Latin exempli gratia. That means, for example. So you interpret, in English it's very used. In Spanish, no.
Yes.
E.g. is for example. And when you have IE is the example. It's like this is, no? This is. That is the interpretation. This is, that is, it means. Okay. Those are the interpretations. Thank you very much. Now let's see Mr. who can participate here. Mr. Jair Ventosilla. The last paragraph, please, Jair.
These tolerances may seem to reflect poor manufacture, but in most circuits they are in fact quite satisfactory. Relaxing the tolerance enables the marker to sell them more
Cheaply.
cheaply.
Yes. So it enables the manufacturer, to sell them more cheaply. Yes. That means at less cost or less price. But there is a problem with the tolerance. Tolerances can be maximum 20%. With 20%, they have established that they wouldn't represent a problem, depending on the type of circuitry. For example, if you are designing some medical equipment or some precise equipment, definitely you need to work with the most accurate components. But if you are working on a, let's say, a circuit that wouldn't represent much problem, having some, let's say, very small or tiny differences in voltage or current, then can be accepted. Now here we have an exercise that consists of, depending on the color, what is the value of the component. No? So we have red, violet, orange, and silver, for example. So number one is established like that. Red, you're going to help me with this table. Remember that we completed the table? So they say here red. So what is red? Red is 2. Okay, 2. That is a value. This is 2. I'm going to change color to notice that we are working with this. Next, we have violet. Violet is what number? From the list, remember? Violet? You have the book there? Yes? No?
7.
Sorry, again?
7.
7. Very good. And then we have here orange. What number is orange?
3.
3. That means that our value needs to have 3 zeros. And then finally we have silver, where silver is
8.
10, no? 10% tolerance. Okay, so we have all of that. Number one means that we are talking about a resistor of the value of 27 kilo ohms. Well, I'm going to copy that because I don't have the going to put number one, some space. I don't have the inserting values, the nomenclature, or I can draw it. Let me see. Okay, let's see. I don't have a graphic tablet, but I can give it a try. The same color. Okay. So we have kilo ohms. Okay. Now that means that with this value, we have a tolerance of more or less 10%. That means that we have to add here and to decrease here 2.7 kiloohms. Now, calculating what is the minimum, what is the maximum. That means that we have the minimum value is, if we decrease or if we subtract 2.7 kiloohms from 27 kiloohms, we obtain, any volunteer to help me? Nobody. Come on, really? 24.3 is okay? What? Kiloohms. No, I cannot take a, we have to copy only. Let's do the copy. And what is that is the minimum. So what is the maximum? The maximum is 29.7. Now, that indicates that just with this simple resistor, the value could go from 24.3 kiloohms to 29.7. Why? Because of the tolerance. That is the gap that our resistor has, our 27 kiloohm resistor has. So quite considerable, yes. But depending on the origin of the circuitry that you are working with or the circuit that you are working with. Now, the other exercises is in the same way. Remember that gold is 5% or 2%. Let me see here. 5% is gold, 5% silver 10%, and when you have no band, for example, in the case of 3 and 4 is 20%. So the difference can be even greater. Okay. Now, clear here the drawings, and let's go to read additional texts. And we are going to see here that there are some values that we are very connected with, or that we find familiar. We are familiar with when we go to places in order to buy these devices. Why? Because those are the most commercial values. No? For example, values like 1 or 1.5, 2.2, 3.3, 4.7, 6.8 are typical. Or 1.2, 1.8, 2.7, 3.9, 5.6 are typical too. Or, well, 1.1 is more specific, 1.6, no, possible to find, but not very common, no? Possible to find, but not common, is because the tolerance is even less. So the preferred values are all these values that are considered in the tolerance scope. So if the maker or the manufacturer tried to produce all the values, it wouldn't be commercially profitable. But that's why the manufacturers decided to have some specific values that are going to be repeated or be constant according to the tolerance percentage. So that is, if the maker tried to produce and sell every value of resistance that exists, that would be chaos, and the cost would be greatly increased. The actual, what is actual? Any volunteer to tell me what does actual mean in English? Is actual mean at present or means something else? Anybody? What does actual mean here? When they say the actual values may therefore are limited to a range called the preferred values. These are listed in the table. Actually, well, not to extend this too much, if you can help me, the new values, not really. Actual means the real values. So those values that you find in the real world. And just in case when they say actually, that most of the times we can confuse this with in this moment actually means really, really, or indeed. That means the real situation is this. So the real values here, the real values may therefore are limited to a range called the preferred values. Yes? Okay. Now the second paragraph says the values may seem illogical at first sight, but this is not so. The stem or the origin from the fact that the tolerance extremes of the value reach the extreme of adjacent values, thereby covering the whole range without overlapping. Values normally available stop in the Megom decade. Okay, that okay. Sorry, I'm back again. Let me see. So I was saying, when you have this overlapping, it is sometimes possible to find this situation. For example, the idea that is established here in the text says this: if we have a line with all the values, we can have the situation like that. Color. Imagine that we have some resistor number 1, okay, resistor number 1, with some specific value. If we extend that value because of the tolerance, the idea is to have that adjacent with other value itself. Going to put with yellow color. I don't know if it is possible to not possible to notice. No? Do other color, the green and this. The idea is to have, I have other value here, green, but when extending this by the tolerance, the idea is to meet the border of the other, trying to cover all the range of resistance. So that is what happens with these values. That is why we have 1.0 connected to 1.5 but 20%. Or we have 1.0 and 1.2 connected by 10%. If we consider, for example, 10%, imagine, this is 1. Well, this is something very easy for you because you are very connected to graphics, etc. So, for example, this is 1, okay? 1.0. Yeah. If we extend that, the 10% is this pink color that is not completely solid. That 10% can meet the other value that is 1.2 by the extension of it. So by the extension, they meet the other tolerance. Then, therefore, they cover all the range of resistance that we need. That is what is established here. So consequently, having the tolerance make it possible not to produce 1.0, 1.1, 1.2, 3, 4, etc. Until or 1.1, for instance. No, we avoid the manufacturing of 1.1. And you can say, well, but it's only 1. Okay, only 1. But if you continue with the range, you have from 1.5 to 1.8, 6, 7. If you go from 1.8 to 2.2, you have 0.9, 2.0, 2.1. So little by little, you are avoiding the construction or the manufacturing of additional resistance values without any profit itself. That is the idea of this. So the question then comes, Why are resistors coded with color bands rather than some other form of marking? Because resistors are such small devices that wouldn't permit other type of efficient marking to know the values of them. What would be the effect of making resistors with a much higher tolerance? Increase cost. Why? Because the circuits may be affected. 1 point or 20% tolerance is practically the top gap. Giving more tolerance, that would be the existence of overlapping. Overlapping is when one resistor covers the other resistor range, which is not very recommendable for circuits. Between which values might a resistor mark green, blue, orange, and silver vary? So green, remember the color band here? Green is 5. And if they say 5, certainly is 5.6. Where is the question? Green, 5. Blue, 6. Let me see. Blue, 6. Yes. Normally is 5.6. So blue, 6, and silver. Green, blue. Green, blue, orange. Orange is 3. So we have 56 kilo ohm with more 10% or less 10%. So those are then discover the values, and that is. Why do manufacturers make resistors in the preferred values shown that rather than equal step values? Because it's not profitable to produce or manufacture one resistor for each value. It's not that necessary. Now, use the following information to name the other devices that also need color bands. That is the case of capacitors. And in capacitors, we find one extra band. The extra band, so band number 1 is the first digit, band number 2 is the second digit, here. Band number 3 is the multiplier, so far the same as resistors. Band number 4, the tolerance, so band 1, 2, 3, and 4 are the same as the resistors. The different band comes here with the voltage, because there is a fifth band that indicates what is the top voltage that they can work with. In the case of red color, they are indicating 250 volts, and in the case of yellow color, they indicate 400 volts. Okay. Now, the exercise here is what are the colors that we need to establish here? And we are going to do one because there is something that we have to consider very important, different from the resistors, and that is that the values in capacitors by default is in picofarad. That means that if you have, for example, let's say the last one, okay? 47 nanofarad. Number 4, what is number 4? Remember the color band? Number
Teacher,
4 is...
I have a question.
Yes, yes sir.
The colors are always the same in all the cases. I mean, in case of resistors and capacitors, are the same, the meaning of the colors?
Yes, yes. The first colors that corresponds to the value, yes. The colors that correspond to the tolerance that you have here, for example, like this. The colors that corresponds to tolerance are different. Now, for example, talking about tolerance, 20% is not similar to the resistor that is not present. In this case, they have a band that is black, or white for 10, or green for 5. They are different. And obviously, the fifth band that you have the voltage colors. But the digits are the same. So 4, what is 4 for resistor is 4 for capacitors too. That is why, in order to indicate this 4, you have to go here, and they say 4. We put here yellow, remember? Yellow. And number 7 is violet. So that means that in our capacitors, in this capacitor, we have the color is yellow here. I'm going to put in black and smaller. So we have yellow. We have for number 7 violet. We have the tolerance is the tolerance here, 20% indicated with black. In the case of resistor, there was no band, for example. So the different colors comes with the fourth and the fifth band. They don't mention anything about the voltage, so we just keep it blank. But something interesting here is with this value, the nanofarad. By default, when we indicate the color bands, we assume picofarads. To nanofarads, we need to add to this value how much? We have to add here 3 zeros, right? If you multiply minus 12 with plus 3, you obtain minus 9, the nanofarad that we need. Consequently, the color bands that we have for this value would be yellow, violet, 3, remember, is orange. So orange. So we have yellow, violet, orange, black. That would be the band color here. So how do we establish this? Well, imagine that this is I'm going to draw here. Imagine this is our capacitor. Okay. With the 2 pins here. Okay. Where the first band, sorry, what am I doing? Where the first band is yellow, the second band, do we have? No, I don't have all these colors. The second band is violet, the third band is orange, and there is a fourth band that is black. So if we put in order, that would be, sorry for my drawing, it's not so precise, but on a board, physical board, it would be better. Yellow, violet, orange, and finally black. No more bands because they don't indicate the voltage itself. But if we had, there would be an additional band. So that is the way. That is established the color coding in capacitors. So we have to study only the colors and that's it? For capacitors and resistors? Yes. Today, there are other forms that are more practical, no? Instead of being or trying to read the bands. That is just using your multimeter and try to measure the capacitance of the resistance. Yes, but it's always welcome and good for you to know the theory behind that. Now, clearing drawings. Is color coding the only way that they mark some devices? No, not really. And that is the case of diodes. Because in diodes, we cannot find, or we don't find color bands. In diodes, we find alphanumeric coding, like, for example, BAX16, BY126, or such long codes like BZX55C2V4, for example. So, in order to mark diodes, we need to check first not only the tolerance or not only the value itself, but we need to be more specific on the material of the semiconductor, the application, the type, and even the voltage in some cases. So I'm going to ask you to read the text. Read the text quickly, let's say 1 minute only, and then we are going to talk about that. I prefer you to read the text on your own first in order to talk about it. Okay, so far they said The first letter corresponds to the semiconductor material, where we have germanium, silicon, gallium arsenide, photodiodes. Then the second letter corresponds to the application. We can have from a general purpose diode to a Zener diode. We have then tuning varicap, tunnel diode, photovoltaic, light emitting diode or LED, control rectifier, varactor, power rectifier. Yes. And just in case there are some kind of, they say, in the case of diodes for specialized applications, no, the third letter does not generally have any particular significance. Zener diodes have an additional letter which appears after the numbers, which denotes the tolerance of the Zener voltage. So the following letters are used. No? They say A, 1%, B, 2, C, 5, and D, 10. Notice that 10 is the top. Now, Zener diodes also have the additional characters that denotes the volts, now the voltage, the Zener voltage. But that is marked with V. For example, 9V1 is 9.1 volts. Then, what are the diodes? With this explanation, I finish here the theory to prepare you for the evaluation. When we have BAX16, letter B is silicon, the material, right? So here we have, this is the material. This indicates another thing. And X16, what is that? We're going to see it. So first is the material. The material is here, B, silicon. Like Silicon Valley, silicon. Now, A corresponds to general purpose. General purpose. And sir, what is X16? This is just a general purpose diode. So X16 is the capsule model of the diode. So practically the model that the manufacturer gives to this. There are different types of diodes according to the models. Now, BY is very similar, but in this case, we are talking about a silicon, and the second letter is Y. What is the Y for? So we scroll, and they say Y is for power rectifier. So that is a silicon power rectifier, the model 126. Number 3, that is the one that I wanted to write, because this diode is a silicon, but the letter Z marks that is a Zener diode. And you can notice that because there are more characteristics. So this is a Zener, silicon Zener. And if you check, you have the letter C. The letter C indicates with some tolerance. The tolerance here, sorry, I'm going to move from here to indicate you. The tolerance C is 5%. 5%. That means that is a silicon Zener diode with 5% tolerance for the Zener voltage. 5% Zener voltage tolerance. And the Zener voltage is also indicated here, 2.4 volts. So 5% Zener voltage, 2.4 volts. And not to confuse with the tolerance here, I prefer to put the tolerance at the beginning. 5% tolerance Zener voltage of 2.4, which is better, not to confuse, which is 2.4 volts. And that is the information that we obtained from a BZX55C2B4. Not all the letters, they have some specific function. One of them or some of them can be the model of the type of the capsule that the manufacturer uses. Okay, so we are going to stop here. For you, please, you will have to continue reading about the diodes. The next point that comes from English is using linking facts and ideas with relative pronouns, which, who, and that. In this case, we are going to refer to which. So how to connect them is the part that we are going to cover the next week for classes. Or on Moodle, I think I can give you an explanation because it's not so complicated. But indeed, the next session we're going to revise this again. Now stop sharing here. I don't want to dispose from your time. Try to adapt your cameras to be activated, please, during all the time of the evaluation. We're going to proceed. I'm going to continue with the recording, as you know, during the evaluation. I have to maintain everybody recorded on this. Now, accessing to the test. This is section N. The topics considered for this test: the internet, programming, future trends, issues in computing. So the last part of computing. Please turn on your cameras, everybody. Turn on your cameras, everybody.